So as we said, the more stable carbocation is formed more rapidly. So it will have a lower activation energy. And this is the reason for the difference in rate. So for example, we have one propene, and the vinyl carbons are carbon 1 and carbon 2. If our hydrogen adds at C1, we form a secondary carbocation. So the hydrogen adds to the carbon that is bonded to more hydrogens. That forms the secondary carbocation. However, the other option that you would consider would be that the hydrogen adds to the carbon with fewer hydrogen bonds. And in that case, that would form a primary carbocation. But as you know, from our list of carbocation stabilities, primary carbocations are much less stable than secondary carbocations. And so the second reaction option does not occur. The hydrogen is always going to add to the carbon that has more bonds to hydrogens. This will always result in a more substituted cation, or at least a cation of equal substitution. What product is formed is going to depend on the formation of the intermediate. Because the secondary carbocation is what leads to having the chlorine at carbon 2 rather than a chlorine at carbon 1. The fact that we form the secondary carbocation is the reason the chlorine adds to carbon 2 instead of carbon 1, and this gives us a different final product. So which carbocation is formed is instrumental in determining what the final product is. Okay. The electrophile adds to the sp2 carbon bonded to the most hydrogens. Our electrophile, when we deal with a halo acid, is hydrogen. And our nucleophile is the iodide ion. And so for HI, if two possible carbocations are both relatively stable, both will form. So our example here is that we have a trisubstituted alkene. And if carbon 1 or carbon 2, I can number the carbons for you. 1, 2, 3, 4. If carbon 2 is the more substituted carbon, and so carbon 2 will form the most stable carbocation by adding, because the electrophile hydrogen will add to carbon 3 and the halide will add to carbon 2. The hydrogen adding to carbon 3, the carbon with more bonds to hydrogen, results in this tertiary cation that I've drawn. If the hydrogen adds to the more substituted carbon, and if it adds to carbon 2 instead of carbon 3, that gives us a secondary cation. The tertiary cation will lead to the major product, but the secondary cation will produce a minor product. So we'll have the majority of our product as the iodide bonded to the tertiary carbon, and then a minor amount of iodide bonded to the secondary carbon will occur. And then we have a second example. So what would the cations look like? You have a positive charge either here or so. The more substituted cation is this tertiary cation. This is a secondary cation, but they both have, well, the tertiary cation is better, the secondary cation is acceptable. And so we form both the major product and the minor product. The major product results from the tertiary cation. And the minor product results from the secondary cation. Okay. Regioselective reactions. These are reactions that form more than one product, more than one constitutional isomer as a product, and the constitutional isomers are present in different amounts. So a reaction can be moderately regioselective, highly regioselective, or completely regioselective. Completely regioselective would be forming only one of the two possible products. Form one of two possible. Highly regioselective is having a major and a minor product. And moderately regioselective would be that the products are present in approximately equal amount. Okay, so let's look at some examples. When our starting material can result in either a tertiary or a primary cation, only this reaction will be more highly regioselective because primary cations are quite unstable. And so the product of a primary cation will not be formed. So this reaction would be completely regioselective. Only one product and the other product resulting from the primary carbocation is not formed. Highly regioselective would be, for example, having a very major product, 90%, perhaps, and a minor product, maybe 10%. So, but we also have reactions that are not regioselective. Here's an example of a reaction that is not regioselective. Both are formed in equal amounts because both of the carbons bonded to at the pi bond have only two bonds to carbon. They're equivalent. They both result in a secondary cation once the electrophile is added. If the electrophile is added to carbon 2, we form a secondary carbocation. If the electrophile is added to carbon 3, we form a secondary cation. And secondary cations are equivalent in stability. So we form both products from the secondary cations in equal amounts. Here's one possible cation, the second possible cation. Both secondary are equally stable carbocation products, and so we form the products in equal amounts. We form both 2-bromopentane and 3-bromopentane. Acid-catalyzed addition of water. This is the second reaction we're going to talk about. done halo acids, and now we're going to look at acid-catalyzed addition of water. I'm going to go and pull up your functional group notebook assignment. So you should be prepared to answer the questions for the, we've done the halo acids, so we should be able to now answer question 1 on the extra assignment for the following drawing. Draw the expected products and include all possible isomers. We at least have an idea of what will occur. We will add hydrogen to the less substituted electrophilic carbon, and we'll add bromine to the more substituted carbon. This will actually form 2 products, and so in terms of all isomers formed, we'll be able to answer that question later. For the functional group notebook, the addition of water to the pi bond is reaction 4, hydration of alkenes with acid. So we started with 1, now we've moved to 4. Hydration of alkenes with acids. So be prepared to fill out that entry on your functional group notebook. Acid-catalyzed addition of water, which we call hydration. So at pH 7, at neutral pH, water does not add to a pi bond. It is not sufficiently electrophilic. This reaction only takes place if an acid is added. We need the pH to be less than 1, as occurs when we add a strong acid such as H2SO4. So our pi bond will break, adding a hydrogen from an acidic proton, forming a carbocation. Then our carbocation will add a hydroxide ion or a water molecule, which will then become deprotonated at a later state. This is going to form the Markovnikov product. What that means is that our new functional group, OH, is adding to our more substituted carbon. The OH adds to the more substituted pi bond carbon. Here's the mechanism of reaction. Firstly, let's look at what is the active electrophile. When we add H2SO4, a strong acid, to an aqueous solution, the H2SO4 will completely dissociate to HSO4- and H3O+. These are the rules of strong acids. We always have a reaction that moves towards the weaker acid, so H2SO4 plus water will form HSO4- and hydronium ion. Hydronium ion will act as our active species that interacts with our pi bond. So our pi bond will donate its electrons to make a bond to hydrogen of hydronium ion. The hydrogen O bond will break and releasing a water molecule. In the second step, our water molecule will bond at the carbocation that was formed when we broke the pi bond. Then so now we've made a new bond to a water molecule. Then this product is a protonated alcohol. This product is not stable. A second molecule of water will remove a hydrogen from the protonated alcohol group, and the bonding electrons of O to H will break and go back to the oxygen. This results in the formation of the alcohol product and hydronium ion regeneration. So hydronium ion in this case is our catalyst. A catalyst is defined as a substance which has the same identity in the beginning as it has in the end. It may change identity as the reaction proceeds, but at the last step it should go back to the same molecular formula that it had at the beginning of the reaction. Acid-catalyzed addition of an alcohol. In this case, instead of adding water to the pi bond, we're adding an OCH3 group. This reaction will form an ether. Acid-catalyzed addition of an alcohol will form an ether. I would say that this reaction almost always ends up on your exam. If we look at the chart of reactions that I gave you to fill out, this should be on that document. I do not believe, it's not part of the functional group notebook, but it is in our files. If you look at the extra reactions that I want you to do, the number 2 is the acid-catalyzed addition of water, and number 3 is the acid-catalyzed addition of an alcohol that results in an ether. So your functional group transformations would be, for number 1, alkene to alkyl halide, for number 2, alkene to alcohol, and for number 3, alkene to ether. So let's look at the reaction where we form an alkene, we change an alkene to an ether. This again will result from the weaker acid, the protonated alcohol. So H2SO4, the strong acid, will react with the methanol in solution to form the protonated alcohol, which will behave as our electrophile. Our pi bond will donate electrons to form a bond to the proton of the protonated alcohol. The bond between oxygen and water will break. This will give us our carbocation with a new bond to hydrogen at the carbon that had fewer bonds to carbon. The alcohol will then act as a nucleophile, donating a lone pair to form a bond to the carbocation carbon, to the positively charged carbon. This will result in a protonated ether. Protonated ether. So we have R is there, CH3 is there, we have CH, and our OCH3 group. So here's the original piece, and here's our alcohol that added. In the next step, another molecule of alcohol will donate a lone pair to remove a hydrogen from the protonated ether. The oxygen to hydrogen bond of the protonated ether will break, sending the electrons back to the oxygen. This results in the final product of an ether. One thing to note with all reactions that go through a carbocation, the major product could be a surprise. If we start, for example, with this 3-methylbutene, and we react with HBr, we can have hydrogen adding to carbon 1 or carbon 2, right? Actually, that's not what happens. We don't form the product where hydrogen adds to either carbon 1 or carbon 2. Well, actually, in reality, what happens is that the initial electrophile does add to carbon 1, the less substituted carbon, but the final product does not have the nucleophile adding to carbon 2. Instead, where does the new carbon bond add? We can number the product to look. So if we carry over the same numbering that we had in the reactant, The carbons would be numbered as follows. Note that the new bond to a bond from C2 to the nucleophile bromide ion, which we might expect to be the major product, is actually a minor product. And the major product results in a bond from carbon 3 to the nucleophile. How is that possible? Carbon 3 already had 4 bonds. This occurs because we have something called a hydride ion shift. We have formed a secondary carbocation when hydrogen adds to C1. So when the hydrogen of this HBr adds to C1, we form this secondary carbocation. But secondary carbocations are not as stable as tertiary carbocations. And it turns out that if there is a hydride or a hydrogen bond to the adjacent carbon that is more substituted, that is a tertiary carbon or a quaternary carbon, then we can have a shift. This is a tertiary carbon. The hydrogen bonded there will shift, including its electrons. When hydrogen shifts, including its bonding electrons, we call that a hydride shift, or H-. So the lone pair, the bond and the hydrogen both move over to carbon 2, and then the positive charge shifts to carbon 3. So when that hydrogen shifts, as shown to carbon 2, we now only have 3 bonds at carbon 3, which results in a tertiary carbocation at that position. This tertiary carbocation will react with bromide ion to form the major product. And the reason that this shift occurs is to form a more stable intermediate carbocation. If it is possible to form a more stable intermediate carbocation, then that will occur. And you will always know if it's possible to form a more stable intermediate cation because you will have within 1 carbon distance a carbon that is more substituted than the original position of the positive charge. Let's look at some more options. Here we have a alkene that has a more substituted carbon 1 bond away from the pi bond. If we draw the skeletal structure, it looks like this. The initial cation has hydrogen adding at carbon 1 and presupposing that the positive charge will form at this more substituted carbon. So our initial carbocation is a secondary carbon. But because we have a more substituted carbon here, we may have a shift. Now in this case, it's not a hydride shift. In this case, it is a methyl shift. So we take a CH3 group with its bond and shift it over to carbon 2. That results in having only 3 bonds remaining at this carbon 3. That gives us a tertiary carbon at that position. And that corresponds to the final product as chlorine will add at that tertiary carbon, or at this carbon here. The secondary carbocation results in only being a minor product. So what we've learned is that hydrides, H with a lone pair, hydride, and methyls, methyl anion, with its lone pair can shift, as long as it results in a more stable, more substituted carbocation.